Hello class. Topic 14. We're going to focus on higher order linear homogeneous ODEs with constant coefficients. Now the methods that we developed for the second order linear homogeneous ODEs with constant coefficients generalize to higher order. So these are differential equations that involve a third derivative or higher. Also, a dth order linear homogeneous ODE has d linearly independent solutions that form its general solution. So we're going to fill in the table below here. And so if we have a differential equation that's linear, dth order, and homogeneous, it's linear because all the derivatives of y and all its derivatives are all in separate terms down to y itself. And each of them is raised to the first. And it has potentially a constant coefficient with a leading coefficient of 1. And then homogeneous because we have equal to 0. So when you create the characteristic polynomial or the auxiliary polynomial, you wind up creating this polynomial right here, and we want to find the d solutions to this equation. And this might involve imaginary or complex roots or purely imaginary or real roots. They might be repeated. And so we're going to we're going to fill in this table here that tells us how to create or find all the linearly independent solutions to the differential equation. Okay, let's do this first one. Let's suppose you have lambda is equal to a is a real root of the polynomial. And let's suppose it's repeated n times. So we're going to be able to create n linearly independent solutions to the differential equation from this one root, from this one real root. And the first one will be, we'll use subscripts to keep track of them. Let's say the first one is y1 is equal to just e to the at. The second one will be multiply by t. So t times e raised to the at. The third one will be t squared, e raised to the at, etc. This would continue. And the last one, the nth one, because we're assuming that this root, which is real, is repeated n times, so we have to create n total linearly independent solutions, will be t raised to the n minus 1 times e to the at. Okay, now suppose our characteristic polynomial or auxiliary polynomial here has some non-real roots, a plus or minus bi. And let's suppose that one of them, or they're repeated m times. So for each instance of this, if you only had one complex number, or one pairing, I should say, complex conjugate pairing, so pretend 2 plus or minus 3i were two different complex roots. So for the 2 plus or minus 3i, that's going to give us two different linearly independent solutions. The first one, I'll call it u, will be e raised to the at times the cosine of bt, where the a and the b are the real and imaginary parts of this complex root. And the second one you get out of this, we'll call this v, but we'll call it v1, is equal to e raised to the at times sine bt. Okay, we saw this be the case when we had just a simple second order linear homogeneous differential equation. But now we're going to suppose, since we can have more roots because we have a higher degree equation we're working with, what if this same a plus bi plus or minus a plus or minus bi is repeated m times? So then we're going to get multiple copies. And each time we want to get a new linearly independent equation, we have to just multiply by a t, an extra t. So this would be e raised to the at cosine of bt, and this next v will be the same thing, but with sine. And we would continue this until we got down to the mth repetition of this complex root. So that u sub m would be t raised to the n minus 1, e raised to the at times cosine bt, and vm would be t raised to the n minus 1 e to the at times sine bt. And I wrote n's here. Those should be m's, because we're stopping at the mth, not nth. So make sure these are m's. Okay. And now let's put this to practice. The rest of the lecture will just be finding general solutions to various higher order differential equations that are linear and homogeneous with constant coefficients. Okay, here's our first one. This is a third degree linear differential equation. And we want to get it all the terms over to one side and get a 0 on the other side. Also, I'm going to double everything at the same time because I don't like working with the fractions or the decimals. So if we double everything as well as move terms around, we'll work with that equation that results. So we have the third derivative minus the second derivative. Then we're going to subtract that 2y prime over, but double it, so minus 4y prime. And then add that 2y over, but double it, so plus 4y is equal to 0. And here is our differential equation. It's linear, third degree, homogeneous, constant coefficients. And now we are going to create the characteristic polynomial. It's just going to be lambda cubed minus lambda squared minus 4 lambda plus 4. We want to solve this for 3 different complex roots because this is a third degree. It turns out we can factor this one by grouping, if you remember that strategy. So if I factor out a lambda squared out of the first 2, and then factor out a negative 4 out of the second 2, notice that what's in each set of the parentheses there is equal, so it can be factored as well. So this just becomes lambda squared minus 4, and then I'm going to factor out this lambda minus 1. If you recall, the factoring by grouping was effectively me putting some brackets around all of this, and those brackets narrowed down to just right there, and I took this pair of lambda minus 1s and factored it out. And lambda squared minus 4 continues to factor, so we have lambda minus 2 times lambda plus 2 times lambda minus 1, and is equal to 0. So this is a clear case where we get 3 different lambdas. They're all real and they're all distinct, so no repetition. So for each lambda that's real, we create an e to the lambda t linearly independent solution. And since they're all distinct, our general solution is going to wind up being constant 1 times e to the, we're going to have 2t, because that's our first lambda, plus constant 2 times e to the negative 2t, plus constant 3 times e to the 1 times t. And this forms the general solution. So all of our roots were real, and none of them were repeated. Let's go to the next one. Now, when you start to get to higher and higher derivatives, usually I stop doing the primes once we get to 3. Once you go 4 and higher, we put the 4, we use a numeral, to indicate which derivative, but you have to put it in parentheses to indicate that it's a derivative. You could also do the Roman numeral and say a 4th derivative like this, or you could do 4 hash marks, and that's also a 4th derivative. But let's say this is a 20th derivative. No one wants to, do something like this. So you would just put a 20 in parentheses. If you don't put it in parentheses, if I just write y with an exponent of 4, this is going to be misread as y to the 4th, which make this technically not a linear differential equation. But that's a 4th derivative. Let's see, I don't need to do any manipulation of all the coefficients are already all real. So I'm just going to move the terms over. We have a 4th derivative. I'll do the IV indication for the 4th derivative. Minus 3 times y triple prime, minus 6y double prime, then subtract that, or add the 28y prime, go in order of decreasing derivative, and then minus the 24y is equal to 0. So here's our linear homogeneous 4th degree and constant coefficients. The characteristic polynomial will be y, or lambda to the 4th, minus 3 lambda cubed, minus 6 lambda squared, oops, not y, but lambda squared, plus 28 lambda, keep writing y, lambda minus 24 is equal to 0. Now, how do we factor this? This one is not going to be factorable by grouping like we did before. There's lots of ways you could do this. You could certainly graph this polynomial and look at the graph and see what the roots are from the graph. I'm going to remind you of the strategy of doing the rational root theorem, which is you look to all the factors, you make a list of possible rational roots of this polynomial, p's over q's, by doing plus or minus. And then you put all the factors of 24 in the numerator. These are the p's. And then the q's are all the factors of the leading coefficient. So the leading coefficient is just 1, so that's all the factors of 1 are 1. But then all the factors of 24, there's a lot of them. We have 1, we have 2, 3, 4. Eventually symmetry will take over, so 4 times 6, 3 times 8, 2 times 20, or 2 times 12, excuse me, and then 1 times 24. So the possible rational roots, well, it's just going to be, because we're only dividing everything by 1, it's just going to be this list of numbers in the numerator, really. Let's get rid of that. So here's our possible rational roots. Now one way to go about finding the actual roots of this polynomial is to use synthetic division. You might recall doing this in a college algebra class. And what I'm going to do is synthetic division. I'm going to go through the roots, plus minus 1, plus minus 2, plus minus 3, and just hunt for the roots here. Synthetic division. So let's start with the positive 1. I'll show you how to do the synthetic division. Let me do positive 2. I already know what the roots are going to be. Let me do 3 actually, because I know 3 is not going to be a root, but I just want to show you the process of the synthetic division. So now you write the coefficients of all the different powers of lambda, and make sure you put zeros in here. If there was a missing power of lambda, let's pretend like this wasn't there, then your coefficients, you would have to put a 0 for the lambda squared. So just be mindful of that when you're using synthetic division, but there is a lambda squared, so make sure we put a -6 there, not a 0. So all the powers, or all the coefficients are accounted for. And then the synthetic division process is, right, the 1 drops, you multiply 3 and 1, you get 3, you add, you multiply 3 and 0, you get 0, you add these, now you get -6, multiply 3 and -6, you get -18, add these, it gives you 10, and then we get a 30, and then add, and we're looking for remainders of 0. And if we get a remainder of 0, that means we've factored the polynomial. And I don't get a remainder of 0 here with using 3, so we erase all that work and start over. Now the numbers that are going to work in this list, plus or minus 1 will not work, 2 does work, -3 works. Let me actually do -3 first. No, I'll do 2 first, because I would have discovered that in the first anyway. So the 1 drops, 2 times 1 is 2, add 2 and -3 is -1, 2 times -1 is -2, add -6 and -2 is -8, -8 times 2 is -16, add -16 to 28 gives me 12, and 2 times 12 is 24, and add that to -24 is 0. That's the remainder. And then this is the quotient. It's a lambda cubed. This is lambda cubed minus lambda squared minus 8 lambda plus 12. And we just want to keep factoring it. And you can keep doing synthetic division. Also, when you first discover that a 2 works, try it again immediately. We're going to now do synthetic division just on that part. But keep trying the same number until it stops working. And that tells you how many times that number is a root. Let's see if 2 works a second time. So bring the 1 down. 2 times 1 is 2. Add to -1 is 1. 2 times 1 is 2. Add to -8 is -6. And oh, sure enough, we got another 0 remainder. Now I'm going to stop doing the synthetic division now because I'm down to 3 numbers here, which means I have a quadratic. So I can find my last 2 lambdas, my last 2 roots, by converting this to a lambda squared plus lambda minus 6. And then just factor that. That's going to be lambda plus 3 times lambda minus 2. So it looks like we have 2 more roots. We have lambda equals -3 and 2, and the other 2 roots were, in fact, let me write them all down. Once you get a remainder of 0, then that's one of our roots. We'll call it lambda 1. Lambda 2 is the other time, so 2 is a root again. Lambda 3 is -3, and lambda 4 is another 2. So this is a case where we have 2 repeated 3 times. So the roots are 2, 2, 2, and -3. And now we're going to construct the general solution. So we have y equals constant 1 times e to the 2t. Now, the second time you repeat 2, constant 2, put a t in front of this, so c2 times t e to the 2t. And the next time that it's repeated, let me move this over slightly, put a t squared in front, so plus c3 t squared e to the 2t. And then we're done with the 2's. Now we shift to the negative 3, so it's going to be plus c4, and we start refresh, so just e to the negative 3t. And this creates our general solution. So looking back at our table, right, when I say lambda is equal to a, it's a real number repeated n times. That one lambda, so like lambda 2 in this case, gave us 3 different linearly independent terms. And then the new lambda, which was lambda equals negative 3, repeated once, gave us the last one, using negative 3 as a. And that's how we got these 4 linearly independent terms. Okay, let's go to the next one. Find the general solution, so another 4th degree. And I'm going to do the synthetic division trick again. 117 doesn't have any factors. 117, when we first write the characteristic polynomial, before we do this, so y to the 4 plus 2, lambda cubed, minus 2 lambda squared, plus 42 lambda, plus 117 is equal to 0. All right, we are interested in finding the 4 roots to this. The factors of 117, well, 117 added 9, and 9 is divisible by 3, so 117 is divisible by 3. You can make a list again of the p's over the q's, but I'll spare you some time. Negative 3 turns out to be one of the roots of this. So I'm going to write down the coefficients. Make sure that you have all the powers of lambda, so you don't need any 0 placeholders. That's very important when you do synthetic division. Okay, bring the 1 down, multiply with negative 3, add these, you get negative 1, multiply with negative 3 is 3, add those, you get 1, multiply, we get negative 3. 42 minus 3 is 39, and 39 times negative 3 is negative 117. So sure enough, that gave us a 0 remainder. So try negative 3 again. Keep trying the same number until it stops working, and then you move on to another guess. So 1 drops down, multiply, add, negative 3 times negative 4 is 12, add that to 1 is 13, and negative 3 times 13 is negative 39, and that gives me another remainder 0. Now I'm going to stop here because I have 3 numbers left, so that means we have a quadratic. This would be lambda squared minus 4 lambda plus 13. You can try to factor it like normal. This one will not factor, so we're going to have to use the quadratic formula to get the last 2 roots. So lambda will equal to negative b, so 4 plus or minus the square root of negative 4 squared is 16 minus 4ac. This is going to be minus of 52 all over 2a. Oops, and a was 1, so 2a is just 2. How does this simplify? We're definitely going to get some imaginary numbers here. 16 minus 52 is negative 36. So we're going to get 4 plus or minus 6i all over 2. So our final 2 lambdas are, divide each of these by 2, 2 plus or minus 3i. All right, so in the end, our roots are, we got negative 3 twice, and then we had 2 plus 3i and 2 minus 3i. If you want, you could lump the last 2 together and just say plus minus. Now, this complex pair shows up only once. It does represent 2 different roots, but as a pairing, it only is repeated once. So in our table, this is like saying we found 2 complex pairing roots, but it was repeated only once. So we're only going to need to create the first row of this. If 2 plus 3i had been repeated twice and m was 2, I would have created 4 solutions by doing, the first 2 rows and get 4 different linearly independent solutions. So in this case, we're going to get 2 of our solutions from the repeated negative 3, and then our other 2 solutions from the non-repeated pairing of 2 plus minus 3i. So our general solution, y is equal to constant 1 times e to the negative 3t plus constant 2 times t e to the negative 3t, because negative 3 was repeated, plus constant 3 times, and if you recall how to do a plus or minus bi, is going to be e to the at, so e to the 2t times cosine, and then the b there is a 3, so cosine 3t. And then plus, I'll just write it here, plus c4 times e to the 2t sine 3t. And here is our general solution. All right, the next one, we have a fifth degree. All right, characteristic polynomial will look like lambda to the fifth plus 8 lambda cubed plus 16 lambda. The y prime is going to be a lambda. If there's no y term here, notice. So because there's no y term, that means there's no constant in our characteristic polynomial, which means we get free factoring out of this right away. I can factor a lambda out. That gives me lambda to the fourth plus 8 lambda squared plus 16. And I can factor the next one. It's a trinomial that factors much like any trinomial you would try to factor it. Two numbers that multiply to 16, which is 4 and 4, but which add to 8. And just double check this, right? Lambda times lambda squared. Lambda squared times lambda squared is lambda cubed. Then we have plus 4 lambda squared plus 4 lambda squared. That's 8 lambda squared, sure enough, and then plus 16. And each of these, I'll just go straight to the roots. We have 3 roots, or we have a total of 5 roots, excuse me. From this lambda here, we get a root of 0. And then from each of these, we get plus or minus 2i. So this time we have a repeated complex number. It has no real part, but it's a repeated complex number. So going back to our table, in this case, the a is 0, because we just have plus or minus 2i. So the a's are 0, so all these e to the at's are going to just go, they're going to go away. They're going to be, because e to the 0 is going to be 1. But then the plus or minus bi, b is 2, that's going to give me the cosine bt, sine bt, but then we're going to have to do a t times cosine bt and a t times sine bt for the second, because it was repeated. So our general solution. For the 0, that's a real root, so we still use this form right here. This a is 0 is real, so y equals e to the at, a is 0, so y equals 1 effectively is a solution of this, but then we put a constant in front. So e to the 0 is 1, so we get just a naked constant that corresponds to this 0 root. Okay, the next one, c2 times, we're going to have a cosine of 2t plus c3 sine 2t. Let me zoom in here and write a little bit smaller. Plus sine 2t. So that's from the first pairing, the plus or minus 2i. Gave me these two linearly independent solutions. But then to get the next ones, c4, since it was repeated, we got to just repeat these, but with a t coefficient. So c4t cosine 2t plus c5 t sine 2t. And this forms our general solution. All right, just one more slide for this lesson. Now we're going to find a particular solution because we have some given data here. And you'll notice this is pretty similar to one of the ones we did before, but it doesn't look quite the same. So let's go ahead and work it out and see what we get. I'm going to convert the differential equation to its characteristic polynomial equation, which is going to be lambda cubed plus lambda squared plus 4 lambda plus 4. This one looks like grouping is going to work as well. So lambda squared, factor that out of the first two. That gives me lambda plus 1. Factor 4 out of the first two. That gives me lambda plus 1. And because the lambda plus 1s in parentheses are the same, we can get lambda squared plus 4 with the lambda plus 1 factored out. And right here I see what our roots are. Make this a little bit smaller. So we have lambda, we have plus or minus 2i, that's from the first factor, and -1 from the second factor. So we have our 3 lambdas here. So our general solution will be y is equal to, let's do the real one first. Let's get that. Oh, let's just go in order. So c1 times cosine of 2t is one of them. c2 times sine 2t is the other. That came from the plus minus 2i. And then the last one is plus c3 e to the -1 times t. So e to the negative t. Okay, now in order to determine what C1, C2, and C3 are, we have to use all this information, which means that we also have to find the derivative of our general solution and the second derivative. So I'm going to do that right now before we go much further. So y prime, the derivative of C1 cosine 2t will be -2C1 sine 2t. Next derivative will be plus 2C2 cosine 2t, and then minus C3 e to the negative t. So there's our first derivative. And the second derivative. Differentiate one more time. We get -4c1 cosine 2t minus 4c2 sine 2t, and then back to plus c3 e to the negative t. Now we want to create a system of 3 equations using this information, plugging it into these 3 equations to create a system. So we know that y of 0. So plug 0 into this, into your general solution. Cosine of 0 is 1, sine of 0 is 0, and e to the 0 is 1. So that tells me we're just going to get c1 plus c3. c1 plus c3 is all we get out of the coefficients. And we know that this has to be 1. That is our given condition here. Now let's plug 0 into y prime. So this will 0 out. Cosine of 0 is 1, so we'll have 2c2. That's going to be, this e to the negative t will be 1, so 2c2 minus c3. And we want that to be equal, looking at this, to -1. And then plugging 0 into the second derivative, this will 0 away. Cosine of 0 is 1, so we had -4c1 plus c3. -4c1 plus c3. And we know that we want this to be 2. Now we have a system of 3 equations and 3 unknowns, c1, c2, c3. You can use whatever methods you want to solve this system. You can use matrices. You can plug the system into a calculator if you're allowed to use technology. Or you can do some substitution elimination strategies, and that's what I'm going to do, in fact. I do like very much that, I noticed that the first equation and the last equation both involve only c1, c3. So these together form a system of 2 equations with 2 unknowns. So I'm going to do elimination on that. And you could do that any which way you want. If I want to cancel the c3s, then I would multiply one of these equations by -1 and then add. Maybe we can do that. So I'm going to multiply this equation here by -1. And let's number our equations. 1, 2, and 3. So effectively what I'm going to do here is I'm going to do equation 1, and I'm going to add to that the opposite of equation 3. So I'm going to just rewrite equation 1. c1 plus c3 equals 1. And then the opposite of equation 3 would be 4c1 minus c3 equals -1. I'm sorry, -2. And the reason I did that was so that I can add the equations together and the c3s eliminate, giving me 5c1 equals -1. So that tells me that c1 is -1/5. And now I can take equation 1 and replace c1 with -1/5 and solve for c3. So we have -1/5 plus c3 has to be 1. So add 1/5 to both sides, and that gives me c3 has to be 6/5. And now we want to find c2. So I'm going to take equation 2 right here. And equation 2 is 2c2 minus c3. So 2c2 minus c3, c3 is 6/5, is equal to -1. And solve this for c2. So add 6/5 to -5/5. That's going to be 1/5 and divide by 2. And we get c2 is equal to 1/10. So here's your 3 c's, and now we can rewrite our general equation with the correct c's. So I'm just going to do a copy and paste. Erase our c's and replace them with their values. C1 was negative 1/5. C2 was 1/10. And C3, which was in front of the e to the negative t, was 6/5. And here we have our particular solution given the initial data. Okay, that wraps up the topic 14 on higher order linear homogeneous ordinary differential equations with constant coefficients.